All right. Yeah, so thank you very much for coming in this morning, especially since yesterday was the excursion day. And I realized that this is a pretty good crowd for a talk about photons at a conference like this. So I am an observational astrophysicist at Texas A&M University. And this week I've been really enjoying learning a lot more about the LISA waveform, about gravitational waves themselves, about the deep physics, and what many of you have been calling sort of the beautiful, neat, elegant world that we see here on the right side of the screen. But it is my job to study what many people have called cloud stars and, stuff that is also in these galaxies. And also on this slide, I compiled some of the other phrases I've heard used to describe the material around black holes this week as a mess. And yes, it can be quite messy. A bunch of stuff in the way. In the way, yes, it is on the way to the center where the interesting things are happening. All this junk, that one stung a little bit, I'll admit. It's not junk. I think I'll show you it's quite interesting and can actually give us a lot of very important information about the elegant world over here. And then this one I agree with, actually. It is a huge pain, especially when your goal is to kind of see through most of it or understand what it's doing that affects these quite straightforward compact objects that are indeed described by only a few parameters. So, as we all know, LISA data is this one massive signal. All week we've seen talks about each of these little subpopulations and how they contribute to the overall LISA waveform. But what some of the instrument people or waveform folks might not realize is that this careful decomposition of a signal this complicated is actually a problem that's quite familiar to EM astronomers. I'm just showing a couple of examples here. Galaxy spectral energy distributions, this is actually a pretty simple one, are made up of stellar populations, gas, AGN, all kinds of contributions and effects, absorption, and stuff along the line of sight. And when decomposing emission line complexes from many different species of molecules and atoms and ions, you can actually have quite a difficult degenerate problem. Light curves are the same way. On the top here in the black is a TESS light curve that is dominated entirely by scattered light from the moon and the sun. And this little bitty dip here is the exoplanet transit signal. After you finally get rid of all that and all these colorful small electronic signals that also dominate. So it's quite a difficult issue, and it's something that EM astronomers have to deal with quite often. So we recognize that the extraction of a LISA signal requires a highly complete census of all the other stuff that's in the way. And all of the other populations that are not your favorite gravitational wave source. So we've been busy for many decades, for our own reasons, building these surveys and encountering challenges and coming up with lots of cool stuff. And I'll talk about one of the first challenges that's most relevant to kind of the headliner LISA science case, but I'll talk about all the others, so don't worry. And that's that binary massive black holes should be everywhere. We think there's one in the center of all these beautiful galaxies, and these galaxies have a tendency to crash into each other pretty often. But they aren't. So there have been many, many efforts over the years to use direct radio imaging. These are emission line spectra, and these kind of complicated shapes of the lines in these spectra have been interpreted as two different emitting regions around two different massive black holes. And then these are light curves with what people claim, I know, to be a periodicity. But all of these things have degenerate descriptions, sometimes more than one. And it is very, very complicated to tell what is a kind of unambiguous signature of a pre-merger binary that is not probably one of these other things. So it makes it very challenging to build a census. The good news is that kind of the era of survey astronomy and the time domain has really made this a more feasible issue. So I'll talk about some of the advantages that time domain astrophysics is giving us in predicting these populations. So here's a beautiful simulation by Jeremy Schnittman showing two black holes with accretion disks orbiting each other, and we're looking at it sort of along the orbital plane or at a low inclination. And what we see is that when they pass in front of each other, the one behind is lensed, and that increases the overall luminosity, or overall flux, coming from the system towards the observer. So this is the predicted light curve. Please don't worry about the axes, it's just time and flux. There is the modulation from the simple Doppler boosting of the signal of the two black holes merging around each other, but imposed upon that are lenses when that fortuitous alignment occurs. Now, this is a sort of a out-of-date simulation. During this very conference on Tuesday, we have seen the advances in this field. This is a simulation of the same scenario up top with much more detailed predictions of the light curve, and you can see much more complicated predictions of the light curve that have incorporated many other expected sources of luminosity and of variability like inclination and the streamers around the black holes and so forth. We do have one candidate. We have one candidate of a self-lensing flare that we found a few years ago. This object is affectionately called Spiky in the literature. They actually let us keep that in the name of the paper. And here is the kind of modulation. The distortion is due to the inclination of the orbit. And here's a zoom in of the fit of the model to the flare. So that's one signal that's less ambiguous than these kind of simple periodic modulations, is having these kinds of self-lensing flares. Another interesting signal is this idea of a centroid shift, and this has really become possible now in mass because of Gaia. So if you have two AGN, but they're not resolved, so you can't see them both, you just see one blob, one unresolved blob of light. As this AGN varies and this AGN varies independently of one another, the photocenter between these two will move back and forth as one gets brighter than the other. In addition, the centroid of that unresolved blob will move wave bands if one of those AGN is brighter or dimmer in the red or blue, depending on its accretion state or Eddington ratio or things like that. So people have been looking for these shifts in the photocenter in Gaia over time and have actually confirmed a large number of binary AGN that are unresolved in the imaging surveys, but that nonetheless give rise to a detectable signature of binarity. Now, there are some caveats here. There's some degeneracies that have to do with lensing, contamination by stars that can cause, the AGN varies, the star isn't varying, and the photocenter shifts. So there are some issues, but most of them seem to be something we can cope with. There's a lot of very recent work using the Gaia data releases to find this, so this is very cool. A different element is not necessarily looking for binaries, but looking for trying to complete the mass function that we expect for LISA. So we've heard some this week about dwarf AGN, intermediate mass black holes. How do we constrain that population when they tend to be less luminous, they tend to be very challenging to detect? And one way of doing that is to look for variability of the nuclear source, which is not what you would expect from a quiescent galaxy. Kind of the pioneering work here is done by Vivian Baldassar back in the SDSS ground-based Stripe 82. Here's 3 galaxies that were not previously known to be AGN, but that have these funky light curves that indicate variability that is like an AGN. And I'll have you just take a look at these light curves. This is 2,000 days, and the sampling's not great. But look at this one. This is only 27 days with sampling every 10 minutes. And this is what's possible with TESS, the Transiting Exoplanet Survey Satellite. Yes, it was designed to look for that tiny little signal of an exoplanet transit, but that photometric precision and the fact that it's in space, so they don't have to skip seasons or daytime, and is above the atmosphere, really gives rise to incredible light curves in the optical, and is enabling searches for small black holes like this one in NGC 4395 in large numbers, especially with machine learning. All right, that's enough of the massive black holes. So, of course, another and perhaps the dominant population in LISA signal is the compact binaries in the Milky Way. So precursor science that will help enable this is a census of binary types and configurations. And we can look forward to this from lots of big ground-based surveys like ZTF and the upcoming Vera Rubin Observatory's LSST survey. And of course, as we observe these systems, we can try and understand from their electromagnetic light curves what's going on with the mass transfer, what's going on with the orbital decay, and what do we expect. And then once the population has been observed by LISA, it helps to, continue to get more precise estimations of the orbital parameters so that we can understand the evolutionary scenario of these objects. And of course, estimating the orbital derivative. So what's happening to the period over time, which lets us understand tidal dissipation and how mass transfer is proceeding, which has implications for the interior equation of state of these objects as well. In terms of the time domain and what it's doing, Gaia and TESS are already discovery engines of compact systems, especially eclipsing systems in the case of TESS. So I'm just showing a few TESS papers here. Here's an AMCVN binary, which is a double degenerate system, 2 white dwarfs or a white dwarf and some other helium-rich compact thing. Transferring mass between each other on very short, this is a 23-minute folded phase, so very short, very fast orbits. Here is a TESS folded light curve of a double eclipsing white dwarf. And here's a neat decomposition of a triply eclipsing triple degenerate system. I think that's this bottom paper here. That was discovered in TESS. There were also very interesting talks on Tuesday by Kevin Burge and Emma Chickles. Emma was looking for type 1a supernova in TESS, precursors to those. So there was very interesting stuff being done with these missions. Kepler, which was the predecessor of TESS, also looked for exoplanets, also made some contributions in this way that TESS is trying to also do. So what we are seeing here is a light curve of a supernova, but before the supernova explodes, zoomed way into the very beginning of as the light begins to rise. And again, we have, this is days, so these are 30-minute samples that are binned. The gray is the 30-minute samples, and the black are binned. And you can see that above the expected theoretical rise, there is an excess of flux, and some modeling has been done to suggest that this is the interaction of the explosion material as it runs into the companion star. And we don't have any information about the companion without this kind of stuff. Kepler was looking for a while before the explosion. And that we don't do. Normally we wait and there's an explosion and everybody points their telescopes at it. So you miss the first part. But the way Kepler and TESS work is these monitoring surveys that are looking all the time. And so you have the opportunity to see this pre-explosion, pre-cataclysm behavior that is new information and tells us about the compact system before the supernova. I realize that EMRIs and EMRIs are different things. This is just a slide about both. I just use the E because that's the one I'm the most familiar with. These are intermediate mass or smaller objects orbiting a supermassive black hole and in-spiraling into that black hole. Now, these will be down at the bottom of the LISA sensitivity band, but still, they're very, very interesting for the potential physics that they can reveal. So precursor science, here are some interesting light curves of tidal disruption events. A tidal disruption event is when a star is eaten by a supermassive black hole. A temporary accretion disk forms around the otherwise dormant black hole. And this is giving us a glimpse of situations where some much smaller object, usually a star, so not usually a compact object that we have yet observed, is consumed by a much more massive object. So that helps us understand kind of the space-time geometry going on here. We can learn more about the expected event rates of these events from large transient-based surveys. What we typically see here, as you can see in the light curves, is a flare followed by a characteristic decline. Follow-up, I mean, we might be able to understand the population of these things, assuming that they are not below the sensitivity curve when the time comes, before the actual merger proceeds. It takes a long time. So that will help us understand and interpret the EM observations during and or preceding and during the event to build a kind of time-resolved movie, if you will, of how these events proceed and what kind of radiation is emitted at each stage. So how are we getting a grip? Slowly, and it's very, very recent stuff. So there is an interesting object right now that I learned about a couple weeks ago. Here we see the supermassive black hole at the center. There's a jet coming out of it. This is post-TDE, so there has been a tidal disruption. A star has come and has formed this nice little disk around the black hole. There is, in this system, an intermediate mass object that is orbiting like this, chilling out, doing its thing. Because the black hole is now active due to the tidal disruption event, it is giving off X-ray emission, that's these blue lines. It's also giving off optical and ultraviolet emission, but it's giving off X-ray emission and is now providing a background, a backlight, to the orbiting intermediate mass object. So before, it was not. There was no backlight. The intermediate mass object was doing its thing, but we couldn't tell. The intermediate mass object sweeps up material as it passes through the cloud of material around the supermassive black hole. It gets caught up in the jet. The material is poofed off. And then we see obscuration along our line of sight to the central X-ray source. Here is the observation with NICER. This is an X-ray timing instrument on the International Space Station. We use it a lot for AGN timing in my group. This is a light curve showing the relative strength of the absorbed portion of the X-ray spectrum versus the continuum, or the backlight. And it has a very significant periodicity. Here's the periodogram at 8 days-ish. This is Assassin 20 QC. So that's one example, but this week there was a lovely talk by Shubham Kejriwal on Tuesday, and also a talk by Joheen Chakraborty, talking about the theory and sort of what we expect here. So here is an intermediate mass object going round and round through the accretion disk. This work in this very recent paper shows the theoretical spectral energy distributions in all these lovely colors, driven by these parameters of the orbiting compact object and the cloud that it's dragging with it. This assumed a black hole mass of 10 to the 6 for the central object. And here in the red star is the mean luminosity of the known 7 quasi-periodic emitters. So these QPEs, quasi-periodic emitters, are the the intermediate mass object candidates, and we have 7 so far, really enabled by time domain X-ray surveys. So we're starting to get a grip here, not just on stellar mass companions or victims, future victims of these supermassive black holes, as we do in tidal disruption events, but actually legitimate extreme or intermediate mass ratio in spirals. So real intermediate mass objects around supermassive objects. Before we move on from TDEs, since the title of this talk is technically multi-messenger astrophysics, although the gravitational waves are already one messenger and the photons are another, so I've covered the brief, but I'd like to at least mention that it is quite possible that tidal disruption events and IMRIs may be important sources of another messenger that we're only just in the past 10 years getting a real understanding of and starting to make sort of like spectra, with very few data points so far, and that's neutrinos. So here is a light curve of an event that was a tidal disruption event that's in the optical light curves in blue and green are optical data points, red and green are the optical data points, blue and purple are infrared from the NEO-WISE survey. That's the new incarnation of the infrared survey explorer that now looks for near-Earth objects and asteroids because it can't get cold enough to do the other stuff anymore. So we see a quiescent galaxy doing not much. We see a big flare that is interpreted as the tidal disruption event, the destruction of the star, the formation of the temporary accretion disk, and then we have a probable neutrino event. Neutrinos can be born from lots of things that happen. Basically, you need to produce a pion. You can do that with photopion production. And if you produce a pion, it decays into neutrinos along a few different possible channels. And there's a few places this can happen. When the streamers of the disrupted star collide with the new captured streamers, you can have shock events that can cause this. If there is a jet a newly born jet that is produced from the tidal disruption event and the newborn disk. Jets are a known source of neutrinos. We've seen at least one very convincing case associating a neutrino with the jet of an AGN that's pointing directly at the observer. That's called a blazar. And finally, cosmology. Now, this is the hardest one to make a pretty slide about, so I just kind of put a bunch of spirals and some ovals. But what I'm trying to get across here is that as we go deeper, as we do deeper and deeper galaxy surveys, we begin to fill in the same survey volume or same survey area on the sky with more and more galaxies at higher redshifts at earlier times. And as we have seen this week many times, the interesting physics and the new fundamental physics that can come from LISA, it really relies upon us having a lot of galaxies early on here, okay? Here's the Big Bang, cosmic microwave background, stars are born, galaxies form, da-da-da. Having galaxies way back here is really important for understanding what we will see in the LISA candidate cosmological signals. So high redshift galaxies that go way back will help us in statistical dark siren analysis. So this is the ability to use gravitational wave signals, use merger chirps from massive black holes as a cosmological tool to measure the expansion or acceleration of the universe, h-naught, without an electromagnetic counterpart. That's why they're called a dark siren. And in order to do this, you need to be able to build a statistical likelihood of galaxies that might be associated with your source, and you're not going to have that right if you don't have enough galaxies in the area on the sky that your source is likely to have come from. Additionally, I have learned this week, which was very cool and set me off on a weird rabbit hole late at night, that some of the new physics that we might encounter, the fundamental physics, such as having a massive graviton, if the graviton is massive, it will cause more dispersion of gravitational waves as the source moves towards us. And understanding the sources of that dispersion means understanding the sources of gravity along our line of sight to the gravitational wave merger source. And that means understanding what galaxy clusters and what massive galaxies are along that line of sight. So this kind of survey science is very important for making it possible to pull out what might be one of the most subtle signatures in the LISA waveform. And that's this new physics or these cosmological phase transitions or the signatures of inflation. So in my last few minutes, I want to show you what kind of surveys are going on right now and what are in the near future. So right now, we're getting a new look at the X-ray variable sky. This is a brand new kind of window with E Rosita. Jeremy Schnittman has a nice poster about X-ray variability signatures in possible binary AGN. Here is a map of the X-ray sky with E Rosita. A very beautiful new look at sources of X-rays across our entire galaxy. And this sky has cadence, so this map is remade. These sources are surveyed with every few days, some portion of the sky is scanned, so we actually have time domain information in the X-rays for many sources. This is brand new. As I mentioned before, the Transiting Exoplanet Survey Satellite, or TESS, is providing rapid optical timing, which is almost all sky. The ecliptic plane is a little bit ignored here. That's because it was hit really heavily with Kepler-2, K2. But they are doing some ecliptic plane fields, I think, this cycle. And this is these strips that you see here, like this is one. TESS looks there for 27 days and takes a reading every 2 minutes. With no interruption, except to send data back to Earth occasionally. There's no big gaps, there's no daytime, there's no issues. So it's a very challenging thing to use test data. I spend a lot of time writing code to do this, but it's an incredible new all-sky optical variability survey. Coming up, we have the Nancy Grace Roman Space Telescope, which is going to do near-infrared, extreme sensitivity near-infrared survey work, which will find lots of high Z galaxies that are very red-shifted. And then, of course, we have LSST Rubin, which is a large multi-band. TESS is only one single bandpass, but with Rubin, we'll have many colors. that's going to survey a huge amount of the sky. There's a lovely poster, and there was a talk by Kevin Burge on Tuesday about what we can expect from the Rubin Observatory LSST survey, which is going to be a transient discovery engine. That's sort of how it's billed, so like tidal disruption flares. But will also be really useful for these kind of binary detection signatures that I've been discussing. So, in conclusion, the search for photons from LISA sources is a monumental worldwide effort based in fascinating problems in astrophysics across all mass scales. For all of your favorite LISA sources, there's tons of questions we have about the actual astrophysics of those sources, the high energy astrophysics, the materials science, and that time domain techniques, coupled with clever machine learning advances, coding technologies, interesting survey approaches are poised to considerably sharpen our understanding of LISA populations, both now, well before, as we prepare, during LISA operations, and afterwards as we seek to understand this complicated waveform. So thank you very much for your attention.
Thank you very much. We have time for some questions. We have someone at the back there.
Yeah, thanks. Very nice talk. About the use of the Gaia data for unveiling double AGN with the centroid. Mm-hmm. So what kind of, if it's possible, what kind of separation would that thing have? And down to what separation you can see this centroid moving around? It's like parsec, kiloparsec, hundreds of parsecs?
Yeah, so it depends, of course, on the redshift of the source, sure. But as long as they have 2 resolved accretion disks within a milliarc second, I think you're in good shape with Gaia, and maybe even lower than a milliarc second. So you can get, but once the accretion disk gets circumbinary, you're in trouble. But until then, I think you're below kiloparsecs in many objects.
Okay, thanks.
Yeah. Yep, just down in front here. Enough. My mic.
I was intrigued by the source you have shown with the spike that could be interpreted as being a lensed disk from a binary. Is this observation really consistent with being this binary very, very tight, so you could really see this enhancement related to this, and or other models that could explain this spike?
Yeah, so the story behind that object is that I had this funky signal in my Kepler survey. I had no idea what it was. I really tried to explain it and couldn't. And then I saw a talk about the self-lensing flares and saw the predicted waveform, the simple one that I showed on the first slide. And I was like, oh, well, this is cool. But the awkward thing was that in that talk, the theorist had said the chances of this happening were very low because you had some, very fortuitous alignment. And I had 30 AGN in my Kepler sample. And 1 out of 30 is way higher than the expected rate that they expected to see for this signal. So we tried to model it as a TDE, as supernova, various other flares, with no luck. It does, the waveform actually is informed by a mass estimate for the black hole from spectroscopy, so it seems consistent with that. But I admit, it would be better if we had more, because it isn't the best of all candidates. It just is, I'm showing it not because it's mine, but because it's the only one. If there were better ones, I would show much better ones.
Yep, down at the front here.
Thanks, Krista, Lynne. That was awesome.
Thank you.
I wanted to ask actually about the neutrino event.
Okay.
So I've listened to lots of the IceCube folks talk about their point back to TX, whatever it is, the one that they think is a supermassive black hole.
TXS
and that's at the threshold of their detection confidence levels and whatnot. But what you were suggesting was when there's an event, right, that we care about, there would be a neutrino burst associated with it. So I was wondering has anyone ever backed out their statistics to try and get at event rates for us?
So yeah, this is complicated by the fact also that what I was showing there, so the blazar you're talking about, TXS0506, that was a spatial, like they had it spatially constrained to the location of that blazar flare. This is just a neutrino event with no spatial information at all that happened to occur time-wise. in the vicinity of this tidal disruption event. So there's not spatial coincidence. It probably is consistent, but if you've seen these things, they're huge. So I think it's work to be done, and Short Van Velsen is doing it. So he had a few of those in the paper. That was the one I found the most piquant. But yes, it's mostly just timing stuff, and we would need to have better spatial stuff to really know what we're doing here. But it's an intriguing possibility.
Great, we have time for one more question, just back here.
Thank you for that very interesting talk. There's one mission that you didn't discuss, and ESA makes a big deal of launching LISA close with Athena. Is there any science that you can do with Athena that you didn't mention?
Certainly, yes. So there will be many missions launched at the time of LISA. Athena, X-ray spectroscopy of transient events that happen when LISA events happen, especially very well-resolved X-ray spectroscopy, will be enormously useful in interpreting the electromagnetic signals, especially if we have accretion disks around the merging black hole. Understanding the iron reflection line or the iron fluorescence line in these two merging systems might tell us something about the spin of the circumbinary disk before the system merges, for example, giving us an actual electromagnetic constraint on some of these cool models with the cavity carved out of the central disk. There's also a very cool electromagnetic signature of an event just pre-merger that I didn't mention. That is the possible disappearance of X-ray flux from the system as the two mini disks tidally disrupt and disperse each other. And there was a nice talk by Kraut about that on Tuesday. So having an X-ray instrument that's able to detect this kind of, a few years pre-merger signature would be really important. Having anything with Athena's capabilities in the sky at the same time as this high-energy astrophysics would be extremely important. And that's not necessarily in the cards otherwise. So, yes, big supporter.
Thank you.
Great, thanks very much. Let's thank our speaker again.